Welcome, future engineering peers. Grab a seat and get ready because today we are kicking off our flagship explainer module on solar energy conversion and photovoltaic systems.
That's right. And listen, whether you're configuring a remote microgrid high up in the mountains or designing a massive utility-scale farm out in the desert, the foundational quantum mechanics and physical laws you'll use remain exactly identical across the globe. Today, we're going to help you master these basics so you can build incredibly efficient, clean energy systems for any international market.
We've got a really packed four-part syllabus for you today. We'll start with global energy and physics, then dive into semiconductor fabrication and generations.
After that, we'll do a live cooperative walkthrough of Example 1A and finally wrap the whole thing up with meteorology and real-world variables.
All right, let's jump right in. Part 1, Global Energy and Physics.
So we are currently in the middle of a massive global shift toward decentralized power grids, and it's fundamentally changing how humanity generates electricity. Think about traditional generation for a second. It relies on these massive, loud, spinning mechanical turbines and combustion. But the photovoltaic effect, it's entirely solid state. It's direct, and it's completely silent.
Which perfectly brings us to the big three solar technologies. First up, we've got photovoltaics, which gives us that direct DC electricity straight from semiconductors.
Then there's solar thermal. These systems capture heat directly and achieve a really remarkable 60 to 70% efficiency. Now you might be wondering, why are they so efficient? Well, it's because they completely bypass the quantum band gap limitations that we have to deal with in semiconductor-based electricity.
Exactly. And finally, we have concentrating solar power, or CSP. Picture this, massive utility-scale arrays of tracking mirrors, heliostats, that focus sunlight onto a central tower to create extreme industrial steam. We're talking temperatures exceeding 500 to 1,000 degrees Celsius. It is literally heavy-duty engineering at its finest.
But let's zoom back into the core PV process. For photovoltaics to work, there is a strict quantum condition for photon absorption. The energy of the incoming photon absolutely must be greater than or equal to the semiconductor's band gap.
Right. If a photon doesn't have enough energy, it just passes straight through the material, like it's not even there. But what if it has way too much energy?
Well, that excess is instantly lost to the crystal lattice as heat. That physical process is called thermalization, and it's actually a primary limiting factor in single-junction solar cell efficiency.
So, once a photon is properly absorbed, it excites an electron and generates what we call an electron-hole pair. But here's the catch. If we just left them alone, they'd randomly wander around and eventually recombine, totally wasting that precious energy as heat. And this brilliantly illustrates exactly why we need the p-n junction. By chemically joining positive p-type and negative n-type silicon, we create this localized depletion region that has a permanent, really strong internal electric field. It basically acts like a directional slide, instantly sweeping and separating those charges before they even get a chance to undergo recombination.
Moving right along to Section 2, Semiconductor Fabrication and Technology Generations.
Okay, it is time to transition from theoretical physics over to rigorous chemical engineering. Let's see how this all builds up from raw materials. Believe it or not, we literally start with raw quartz sand, silica. First, we heat it with carbon to strip away the oxygen. But honestly, that's just not pure enough for what we need. Through a super intense chemical purification called the Siemens process, we vaporize and distill it until we reach what engineers call 9 nines purity. That is 99.9999999% pure electronic-grade polysilicon. We have to be that precise because even one microscopic impurity could cause massive electron recombination. From there, if we're building premium cells, we use the Krzyzewski method. We dip a little seed crystal into a crucible of molten silicon and slowly pull and rotate it upward. This grows a perfect, massive, single-crystal cylindrical ingot.
Next up, those ingots are sliced using diamond wire saws into ultra-thin wafers. During the actual semiconductor fabrication, we use chemical etching to create literally millions of microscopic surface pyramids. This is a neat trick. It traps the incoming light and minimizes reflection. Then, we apply a really thin silicon nitride anti-reflective coating, or ARC, via plasma deposition. This is actually what gives the solar cell its iconic dark blue or black color. Plus, it passivates the surface to drastically reduce electron recombination. Finally, we screen print silver fingers on the front and aluminum contacts on the rear. That's what actually collects the current so we can use it.
Now, let's contrast the commercial technology generations currently out on the market. Generation 1 is your classic crystalline silicon. Premium monocrystalline leads the pack with 19 to 24% efficiency, superior low-light performance, and that sleek uniform black look. Polycrystalline is cheaper, hitting 15 to 18% with a speckled blue look, but it's rapidly being phased out. Then we have Generation 2, which features thin film technologies like cadmium telluride. These are absolutely incredible for hot environments because of their high absorption coefficient. But Generation 3, that is where the engineering future is heading. We're talking bifacial modules capturing ground-reflected albedo light and emerging perovskite silicon tandem cells that layer materials to totally shatter single-junction limits and push well past 30% efficiency.
All right, let's put this into practice. Section 3. Cooperative walkthrough of example 1A.
Okay, everyone, get those lecture notes out and fire up your calculators. Let's anchor the starting laboratory metrics for this monocrystalline silicon module under standard test conditions. Pay close attention to these numbers. Write them down as we go. The active area is 0.016 square meters. The irradiance is a perfect 1,000 watts per square meter. The short circuit current, or ISC, is 6.40 amps. The open circuit voltage, VOC, is 0.62 volts. And for our operating peaks, the voltage at maximum power point, VMPP, is 0.52 volts and IMPP is 5.80 amps. Let's run the math together.
Step 1. We need to calculate the peak operating maximum power output. To find this, we simply multiply our operating voltage, VMPP, by our operating current, IMPP. That is 0.52 volts multiplied by 5.80 amps. Punch that in, and you get our peak power delivered by the cell of exactly 3.016 watts.
Step 2 requires evaluating the fill factor, or FF. This is a super important metric because it evaluates the squareness of the IV curve by comparing your actual max power against the theoretical upper bound. It diagnoses internal parasitic losses.
So we take our maximum power of 3.016 watts and divide it by that theoretical maximum, which is VOC times ISC, so that's 0.62 volts times 6.40 amps. The result is 0.7601. This means we have a highly efficient fill factor of 76.01%. Internal resistance is low, which is exactly what we want to see.
Step 3 brings us to the overall conversion efficiency. First, we have to calculate the raw solar power input actually hitting the cell surface. An irradiance of 1,000 watts per square meter multiplied by our 0.016 square meter area gives exactly 16.0 watts of raw input power. Finally, to get our efficiency, we divide our electrical output of 3.016 watts by that 16.0 watts of raw input power. Multiply that by 100, and we establish a final overall baseline conversion efficiency of exactly 18.85%. Great job following along.
Time for our final section, Section 4, Meteorology and Real-World Variables.
Fantastic work on the math back there, but now we really must shift our academic focus back to the real world. Because in the field, sunlight isn't perfectly uniform. It actually follows a fluctuating bell-shaped daily irradiance curve.
Right, and engineers have to simplify this. We use a standardized metric called peak sun hours, or PSH. One peak sun hour is equivalent to 1 kilowatt per square meter of solar irradiance for exactly 1 hour. It's brilliant. It basically turns a messy, unpredictable bell curve into clean, standardized mathematical blocks that we can easily use for system sizing and daily energy forecasting.
But capturing that energy requires some strict array optimization rules based on geography. First up is azimuth. If you are operating a system in the southern hemisphere, your panels must absolutely face true north to maximize that daily energy harvest. No exceptions. Second is inclination. Your structural tilt angle should roughly equal your geographic latitude. This perfectly balances the differing summer and winter sun trajectories. And third, shading. You must avoid obstructions at all costs. Because internal cells are wired in series, think of it kind of like a long water hose. Obstructing just 10% of a panel can actually slash your entire string's electrical output by 50% or more if those bypass diodes don't engage.
Finally, remember that your pristine theoretical DC output is absolutely going to drop due to real-world variables. We're talking thermal heat degradation, soiling and dust building up on the glass, and ohmic wiring limits. We measure all of these real-world losses using the performance ratio, or PR. It's the ultimate metric for evaluating how effectively a PV plant converts the available solar resource into usable AC electricity. A well-designed modern commercial installation typically hits a performance ratio somewhere between 75 and 85%.
And that brings us to the end of our foundational module. You now understand the quantum physics, the incredibly complex semiconductor fabrication, and the rigorous mathematics governing solar energy.
So, as future engineers, we want to leave you with an inspiring challenge. As third-generation tandem cells completely push single-junction limits past 30% efficiency, how are you going to apply this knowledge? How will you engineer the decentralized grids of tomorrow to master this incredible raw power? Keep innovating out there, and we'll see you in the next session.